So, in this lecture we continue our discussion on the Verilog language. If you recall, in our last lecture we were talking about finite state machines, and we had said that we will be seeing that how we can model such finite state machines using Verilog. Now, we had mentioned that there are two broad classes of FSMs, two types, Moore machine and Mealy machine. The essential difference between these two, just to recall, is that in a Moore machine the next state of the sequential circuit depends on the present state and the presently applied inputs. Okay. But whereas the output, these are the outputs of the circuit, the outputs depend only on the present state and is independent of the applied primary inputs. Now, in contrast, a Mealy machine has both its next state and the output functions depending on the applied inputs and the present state. Next state depends on these two through a logic called the next state logic. Similarly, the output logic generates the output as a function of the present state and also the input. So, we will see that how we can model both these classes of machines, Moore and Mealy, with the help of some examples. First, let us talk about a Moore machine, where the output can be directly derived from the state without any reference, or means without using the present value of the primary inputs. Okay. So, the example we take to illustrate the modeling of a Moore machine is a simplified version of the traffic light controller. Now, here what we assume is that we have something similar to a traffic light controller, but instead of going into the complexities, just for the sake of illustration, we assume that there are only 3 lamps or lights we need to control, red, green and yellow, and without loss of generality we assume that the 3 lights has to be displayed or glowed cyclically at equal intervals of time. Well, means in practice the times will not be equal, of course, but for the sake of illustration we assume that they will be glowing cyclically at a fixed rate. These are the simplifying assumption. We have only 3 lights. So, we consider only one road junction, only one road. So, only 3 lights we need to consider, red, green and yellow, and we assume for the purpose of this example is that these 3 lights glow cyclically at a fixed rate. Now, this rate can be anything. The rate is determined by this applied external clock. This clock can be as slow or as fast as we desire, and these lamps will be glowing cyclically along with this. Fine. So, now let us see how we can model this using Verilog. Okay. This is the first part of the code for the module. So, we have the traffic light module which takes an input which is the clock, CLK is the input, and the output is lights. Actually, light is a vector, you can see it is a vector of 3 bits. So, actually there are 3 lights, this is your light. Now, depending on which light is glowing presently, this circuit clearly can have 3 different states. Now, in this program we are classifying these 3 different states as 0, 1 and 2 in terms of the internal state variables, and we call them S0, S1, S2 by this parameter constant definitions. So, the 3 states will be defined as S0, S1 and S2. Now, means our interpretation is like this S0, in state S0 we will assume that the red light is glowing, in this state S1 we will assume that the yellow light is glowing, and in S2 it will be green. So, these are the interpretations of the different states. Okay. So, now let us see the code. Now, the 3 lamps which are glowing, this we assume that the first one is red, the middle one is green, this one is yellow. So, again this 3-bit pattern of the light 1 0 0 0 1 0 or 0 0 1, well 1 means the lamp is glowing, 0 means it is not glowing. So, these 3 we again define as a constant parameter. Red we call 1 0 0 as red, 0 1 0 as green and 0 0 1 as yellow. These names we have given just for the sake of convenience, for nothing else. And since the machine, the FSM can be in one of 3 different states, we need minimum 2 state variables or 2 flip flops to store the state. That is why the internal state we are representing as a 2-bit vector. It is of type reg of 2 bits. Now, here the states are changing always in synchronism with the clock. We are assuming that they will change at the positive edges of the clock. So, the code goes like this: always at the positive edge of the clock, we do a switch based on the value of state. Suppose we are currently in state 0. State 0 means the red light was on. So, now if a clock comes, we have to light the next one yellow. So, if it is state 0, then we will have to go to the next state. The next state, the way we go is that we first store this yellow pattern into light, so that the yellow light glows, and S1 will be the new state now. Okay. So, to continue this, similarly, if you are in state S1, this is yellow. So, if a clock comes, the next state will be green, which is S2. Similarly, if you are in S2, if a clock comes, you will go to red. Red means S0. And if you, means at the initial state when you start the machine, if the state variable becomes by mistake 1 1. So, in order to set it to red, you set the default clause also. If it is default, the light will be red and state will be S0. So, by default you always start with red. Okay. Now, we look at this code once more. You see the way we have written this code, of course, we have given a always block with a clock triggered event. So, this will be modeled as a sequential circuit obviously, and these assignment statements are non-blocking. This will imply that the light and the state, these variables where we are storing the values, these will be synthesized as registers, as flip flops. Okay. So, this solution will be having the following characteristics. There will be 5 flip flops which will get synthesized, 2 for the state variables and 3 for the lights, right. But one thing you understand, the lights which are being generated, these are stored in some latches and from there they generate. Let us again come back to this code. This light, we are storing this red pattern into this light variable and S0 into the state variable. Now, this light variable, this by definition, the way you have written the code, this is defined as a register and this pattern will get stored into a register. So, this is how the synthesis will take place. But suppose we want to carry out the synthesis in a way where we get, or means we specify that the lamp should be driven like this. Suppose we have this state, say this represents the present state, the 2 flip flops. So, whatever is the present state, well, I can always design some combinational circuit out here, and from this combination circuit I can generate those 3-bit pattern red, green, yellow. So, really we do not need a separate latch out here to store the value and from there to drive the lights. This part of the circuit can be a combination circuit alone. So, Now, let us see that how we can specify that. So, means actually what we want is that we want non-latched outputs. The states have to be latched anyway, the states will have to be stored in flip flops, but the outputs which are getting generated, we do not want any latches out there. So, if in modeling a Moore machine we do it in the way we have just shown, then the outputs will be latched by default. But if you want non-latched outputs, we have to change the Verilog code in a slightly different way. The thing we do is that we use two separate always blocks, one for the state and one for outputting the light combinations, and one of them will be non-blocking, one of them will be blocking. Let us see how. So, we make some changes to the Verilog code. We do something like this. The first part is the same, there is no change here, but after that whenever the clock comes, we are dividing this into two parts. So, means in the earlier code both the state variable and the lights were assigned inside this same always block, but here in the first always block we are only using this for state changes. If there is a positive edge of the clock, if the state is S0 then go to S1, if it is S1 go to S2, S2 then go to S0, default go to S0. So, here we are only modeling the state change behavior, and since this is non-blocking assignment, so this will imply that there will be two flip flops synthesized for, you can say, storing the state. But we have not mentioned anything about output here. Now, output we will be specifying in a separate always block, and that always block need not be triggered by the clock. What we do is that the second always block we trigger it by change in the state, because change in the state will be taking place anyway in synchronism with the clock. So, here indirectly we are specifying that whenever there is a change in state, you execute this block, and you recall this is a non-blocking assignment, sorry, blocking assignment equal to. So, blocking assignment normally if it is not triggered by a clock, this is synthesized into a combination logic. So, if it is S0, this red pattern is stored in light, if it is S1 yellow is stored, if it is S2 green is stored, if it is default red is stored. So, if you specify in this way, then what will happen is that the output generation logic synthesized as combinational circuit. So, if we really want this, normally in a Moore machine we want this. Moore machine there is no point in storing the output in a latch, because anyway the output can be directly derived from the state. It is better to have a combination logic to do that. Okay. So, for a Moore machine this is a good idea, or this may be the better way to specify the next state function. Okay. So, let us take another example of a Moore machine before moving to an example of Mealy machine. Okay. So, the example we take is a serial parity detector. Well, here we assume that we want to design a circuit block like this, which will be having a bit stream x. X is a stream of bits, serially it is coming in. It may be 0, 1, 1, 0, 0, 1, 0, anything is coming, a stream of bits is coming, and they are being fed to the circuit in synchronism with the clock. The output Z will be continuously monitoring the parity of the bit stream which has been seen so far. 0 will be for even parity, 1 will be for odd parity. So, as the bit streams are coming, the streams of the parities will be coming out continuously. First for 0 it will be 0, 0 1 it will be 1, 0 1 1 it will be 0, 0 1 1 0 it will be 0 and so on. So, it will continuously compute the carry of the bit stream that has been seen so far, and the output in the next time instant will be the corresponding parity value. This can be very easily modeled by a state diagram like this. So, here we have two states, we are remembering the state, whether the bit pattern we have seen so far has a even parity or a odd parity. These are the two states. So, if it is even parity and an input 0 comes, it remains even. If it is odd and an input 0 comes, it remains odd. Well, only change takes place if the next input is 1, then even becomes odd and odd becomes even. Okay. So, this example illustrates that I have an FSM modeled as a state transition diagram like this or a state transition table. From there I want to write the Verilog code.
So, the inputs are coming from the left hand least significant.
No, input is from this order. I am just assuming one by one. Okay. So, the way we write the code is like this. Parity generator, this as I mentioned, x and clock are the input, z is the output. Output I am declaring as reg, and this is the state. I am calling this state even odd. Since there are only two states, one variable is sufficient. And even or odd, I am calling 0 as even and 1 as odd, and using parameter I am giving the names of these constants. Now, let us see how what we do. Always whenever there is a clock, we are checking the state and doing accordingly, case even odd. If this state is even, then you again come back to that diagram, previous diagram. If this state is even, then if the input 0 comes, we will remain in the same state and also the output will be 0, because this even means output is 0. Okay. So, you see in this code, if it is even, we are first thing we are doing, we are given a conditional, if x is true then 1 else 0, exactly what is specified in the diagram. Similarly, for the next state, if x is 1 then go to odd else even. Okay. So, here the style of modeling is the last one, the means in fact the first one we have mentioned using non-blocking assignments, where both the output logic and the state will be synthesized as flip flops. Similarly, if the state is odd, we do a similar thing. If x is 1, then we go to the other one 0, else 1, this will be the output, and state, if x is 1, then you go to even, otherwise you go to odd. So, this style models the first one, where both outputs and states are synthesized as flip flops. But if you do not want that, then you can again break it up into two always blocks, as I had mentioned earlier, you can do the same thing. So, if you do not need the output latches, then you can follow the principle in the last example, whereby you can use two different always blocks. Well, in means one always block you can trigger by the pausage of the clock. So, here you will only be changing the state, there will be another always block. So, here you will be changing that only when that even odd changes state. So, here, so next state computation will be here and the output computation will be here. So, you can do the same thing.
So, in the first example, sir?
Yes.
So, the output depended on the input, x.
In the first example, the output was dependent on the input, but here there whatever is the state, that same thing you can take as the output. The combination circuit is just a wire, nothing else is needed. But in general, you can need some transformation.
So, in the first case, as we had modeled, it becomes a milli machine because x depends on.
Milli machine means the output depends also on the primary inputs, but in that example, was it depending on the primary input?
Like in this example, x naught is the input. So the output stage is dependent on x naught. The input stream comes like.
No, not really. Let me try to clarify. See, here what we are actually designing is a serial parity detector, right? Serial parity detector. Let us take an example and illustrate. Suppose this is the bit, okay, this is the first bit which is coming, I am showing from this side onward. This is the first bit which is coming. Suppose the bits are coming in this way. This is what I am calling as x, and state odd even, I am trying to write odd even. Depending on whatever you have seen so far, this state will be set accordingly. So, I have seen 0, that the state is even 0, 0 1 state is odd, 0 1 1 state is back to even, odd, 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 even. So, these are the states. Now, you look at the model of the Moore machine again. There is a next state logic. Next state logic generates the next state in response to the present state and the present input. But in this example, whatever is the present state,
So that is the next state is determined both sides.
so from state you can directly derive the output. For the output you do not need x, this is what I mean. So, this you can categorize as a Moore machine, this is not really a Mealy machine.
But the way we wrote the code, it looked like.
The way you wrote the code, it looked like Mealy machine. We tried to mix them up, but actually the way it is working, it is independent of the input. Whatever state you are in, from the state you can directly derive that is what should be the output at the current point. Okay. Fine. So, now let us take an example of a regular Mealy machine. So, here we take a slightly more complex example, a sequence detector. So, a sequence detector, this is the state transition diagram. We want to detect this sequence 0 1 1 0 in this input pattern x. This x is again a serial bit pattern coming in synchronism with the clock, and z is the output. Now, here what I mean is that, what I really want is that, suppose, well, I am writing from left to right for convenience. Suppose I have a, well, I want to detect 0 1 1 0, okay. Suppose I have a pattern 0 0 1 1 0 0 1 1 0 1 1 0 0, suppose. So, the output z will be detecting the first 0 1 1 0 pattern here. So, the output will become 1 here. It will detect the second 0 1 1 0 pattern here. So, second time the output will become here 1 here, and we are also, the way we will be designing, we will also be allowing overlapping patterns. So, the third 0 1 1 0 pattern will be this one, overlapping with the previous. So, the third time the pattern will be detected here. This is how we are going to design the machine. Okay. So, here we will be allowing this overlapping pattern also. 0 1 1 0, the last 0 of the previous pattern can be the start of the next pattern, right. Let us see now. Just we will look at the state diagram, you will understand. S0 is the initial state, we do not know anything. Well, we get a 0, we move to S1, we get a 1, we move to S2. This is the input slash this is the output. So, we go to S0, we get from S1 S0 to S1, if the input is 0 and the output is 0, because we have not seen the entire pattern as yet. Similarly, the next one leads us to S2, the third bit leads us to S3. Now, when we get the final 0, well, we have detected the pattern, but instead of going back to S0, we go back to S1, because this 0 is possibly the beginning of the next pattern, we do not know. That is why we move back to S1, not S0, and here you see that the output is 1. But if you have otherwise, say while in S1, S1 means I have seen the first 0. Now, if a stream of zeros comes, I will remain in S1 because I have seen the 0. S2, if a 0 comes, I again come back to S1 because I again start with the first 0. From S3, if there is another 1 comes, I will again have to begin from S0. In S0, if a 1 comes, I remain here. So, this is the state transition diagram I want to model. Now, you see in this example, the output which is being generated, that does not only depend on the state, it also depends on what input we are getting at that point in time. For example, while in S3, if the input is 0, the output is 1, if the input is 1, the output is 0. This is what Mealy machine is all about. So, the outputs are also dependent on the primary inputs. Okay. So, the way we can model this is as follows. First part is similar, we have 4 states, these we denote as 0, 1, 2 and 3, we call them S0, S1, S2, S3. We have the present state and next state, both they will have to represent by 2 bits because there are 4 states, and we use 2 different sets of always blocks. This is the style to be followed for Mealy machine, you just note. In the first one, we simply give an always block where whenever there is a clock, the next state gets transferred to the present state, nothing else. The next state becomes the present state. There is another always block where we are triggering by any change of the state or any change of the primary input. Depending on which state we are in, we are computing the output, we are computing the next state. Let us try to understand what we are doing. In the model of a sequential circuit, well, I am drawing it in a slightly different way. You have a combinational part, this is the combinational logic, this is your primary input, this is the primary output, and you have some state variables here. Okay, let us call it S. So, the output of the combinational circuit is being fed here and this is fed here. So, this is your present state and this is your next state. So, both the primary output and the next state will be some function of primary input and present state. Now, if you look at the code, in the first always block, we are simply assigning next state to present state whenever there is a clock. So, what it means with respect to this diagram is that clock is only coming here. Whenever there is a clock, next state gets transferred to present state. No other computation is clock driven. Computation of primary output, computation of next state, that is purely through a combination logic, that you can compute continuously, but whenever there is a clock pulse, this ns value will come to the output of S. Okay. That is why for computing the primary output and the next state, we have used another always block. Okay. Now, in this always block, depending on the state, we are computing the primary output, we are also computing the next state. Now, these we have directly taken from the state transition diagram, that if you are in state S0, then if the input is x, then the output is x, otherwise also output is 0, output is 0, otherwise also. Next state, if the input is 1, you remain in S0, if the input is 0, you move to S1. Just from the state diagram you can directly code this. So, in a similar way you can code the output transition and the next state transition for all the different combinations. So, this is S0, S1, S2 and S3. So, actually what we get finally will be a circuit like this, where only the state will be coded as flip flops, and these since we have coded as blocking assignments, they will be mapped into combination logic, not sequential circuits. So, the generation of primary output and next state will be through combination logic only. So, if you follow that particular design style, you will be getting a circuit where you will be, well, the model will be like this, like conventional circuit. So, the state generation will be through flip flops and the remaining will be through combination part. Okay, fine. So, now that you know that how you can model a Moore machine and a Mealy machine, suppose I give you a state transition diagram, you can write the code. If I give you a state transition table, which is another way of representing the diagram, state transition diagram, you can also do it. But if I specify the FSM in any other way through a set of if then else statements, for example, then also you can directly translate it into a Verilog code. So, any FSM if you have in whatever way, you can code it in FSM in the language Verilog. But it depends whether you want the output to be latched or unlatched. So, the kind of assignment statements will be giving in the always block will depend on that, blocking or non blocking. Okay. So, the one last example we will be discussing today in this lecture, that is an example where we will be showing you some kind of modular design or some kind of hierarchical design. So, means any big system design, suppose we want to design a system which is relatively big. So, a natural way of designing will be to break it up into smaller pieces or smaller submodules, design the submodules individually and then try to combine them up. So, I will try to illustrate with a simple example that how this is done. Now, this is a hypothetical example. I have again taken this for the sake of illustration. This is one example where, as you can see, we have 3 different identifiable modules. Now, actually what we want to do is that we have a adder subtractor and we want to check the parity of the result. So, actually what we want is something like this. We want to design a block which will accept 2 input vectors A and B. There will be a control signal at sub, and there will be an output called P. So, the specification of this block says that this P will be, this P is the parity of either A plus B or A minus B. Now, whether you are adding or you are subtracting, that is determined by the control signal. So, internally either these 2 numbers are added or subtracted and then the parity of the result is computed. Just a hypothetical example I told you, in practice you may not be needing such a thing to compute the parity of the result. So, naturally we can partition the design into 3 parts. We need both addition and subtraction. So, we will be using an adder and we will be using a complementer in case we need to do the subtraction. Now, adder will be taking A as one of the inputs and it will be taking either B or the 2's complement of B as the other input. Well, not really 2's complement, it is actually 1's complement. And this add sub control signal, if it is 0, this means add. If this is 0, 0 means add, 1 means subtract. So, if it is 0, then the complementer will straight away pass the input to the output, and also the carry into the adder is the same signal, that is also 0. So, simply we are calculating or computing A plus B. But if the signal is 1, then this complementer will be complementing, or it will take the 1's complement of B. B out will be the 1's complement of B. This bit is 1, so another extra 1 is getting added. So, this 1's complement plus an additional 1, which means 2's complement is being added. So, A plus the 2's complement of B. So, the output will be the subtraction A minus B. And finally, there will be a parity checker module, which will be computing or calculating the parity of the result, and it will be sending out the result out here. Okay. Now, let us try to see the different blocks out here. We start with the complementer. You see, the complementer takes input and output as vectors and takes one control signal, okay, whether to complement or not complement. Now, in this design, we are assuming that all the operands are 8-bit quantities. So, the complementer, as is being specified in this module, that the input x is an 8-bit quantity, vector 720, output y is also an 8-bit quantity, and there is a control signal called comp. Here we are giving an always block that whenever x changes or the control signal changes, if the control signal is 1, then you complement the output y is equal to naught of x. Naught means bit by bit inversion, this x is a vector, else x equal to y. So, this is a condition where you are specifying all possible values of the comp, means what to assign. So, this will be synthesized as a combination logic. Now, the logic that will get synthesized out here will be something like this. There will be an array of exclusive OR gates which will be synthesized. These are the x inputs, these will be the y outputs, and the second input of the XOR gate, that will be the control. This is comp. So, you know that in an XOR gate, if one input is A, say the output is F, and this is say C. So, if C is 0, then F equal to A, and if C is 1, F equal to A bar. So, we are following that same principle here. Well, so actually when the synthesizer will be analyzing this code and will be trying to synthesize, it will be synthesizing like this, because the way the logic functions will be generated after analyzing this will be the XOR function, there will be all be the XOR functions. So, the synthesizer will be intelligent enough to synthesize it as an array of XOR gates typically. Okay. So, after the complementer comes the adder. That is very simple, it takes two inputs and a carry in, and it generates a sum and a carry out. So, sum and carry out are the outputs and these three are the inputs. Now, the inputs are 8-bit quantities, sum is also an 8-bit quantity, carry in and carry out are there. Sum and output are declared as registers. Now, here whenever one of the inputs changes, we are computing this. So, this is a behavior level description you are giving at a higher level, in1 plus into plus carry. So, at least for addition behavior level description is acceptable, because well as a designer it is good if you have some idea as regards to what kinds of modules are available in your library, because you know that simple modules like adders, subtractors, multipliers are already available. So, addition you need not specify in a structural form, in the form of gate level interconnections and so on. You can simply specify the behavior, and the synthesizer will be picking up the best adder it finds out from the library and put it in. This is a combination logic only. Yes. Since it is combination logic, you can do it with assign also. Yes, we can do it with assign also. It does not make a difference, because this always block. This always block here out here. This makes sense only for the simulator, but for synthesis always block, or you can give assign also. They are the same. So, these three values are getting added up, and we will be getting a 9-bit result, sum, and possibly a carry out. This is a concatenation. This is how you specify. Okay. And finally, you have the parity checker, right. So, in the parity checker, well, you can simply specify it in this way: module parity checker, this is the output. So, the input will be a vector and the output will be a single bit, and input in that circuit it is the concatenation of the sum and the carry, it will be a 9-bit quantity. So, here this will be a 9-bit quantity, and output will be output. This is the output. So, this is inward and this is out pair, and whenever the input changes you are giving a reduction operator. Reduction operator had said an operator before an operand means you take a bit by bit operation of that and you generate a single bit out of it. This means it is bit by bit XOR. You take XOR of all the bits, that will be your parity. Okay. So, you get this. Okay. So, now with respect to this design, we have specified all these three blocks: complementer, adder and parity checker. But what we have not specified as of now is that how these three blocks are interconnected together. That is what we need to specify. So, in any design where you have some kind of a hierarchy, you will be designing the low level modules fine, but you will also have to design a top level module where the low level modules are picked and placed and interconnected. So, this is the example top level module for the circuit we are discussing presently. So, the name of the module you are giving as at sub parity. This is the name of the top level module, and in the highest level this module takes 3 inputs A, B, then at sub, and it generates an output P. This is at the highest level. So, these are the interface specifications. See, internally whatever you do, suppose overall you are trying to design a block like this where A, B, at sub and P are the input output points. So, at the high level the whole thing will be treating as a black box, and you will be seeing what are the interface pins or signals and what are their sizes. So, in the top level module you have to specify all those here. These are the signals or the wires or the pins, whatever you call, that will be coming in or going out of the module, which you, if you treat it as a black box. Now, if you go into slightly more detail of this, firstly you will have to specify the sizes of each of these. So, AB will be 8-bit quantities, at sub is a single bit, similarly P is a single bit. Now, internally, now since you have this structural diagram already with you, you know that there are some intermediate signals you need like B out, sum, carry. These signals are not available to the outside world, but used internally. B out and sum are 8-bit quantities, carry is 1 bit. So, here we declare B out as sum as wires 8 bits, carry as a single bit wire. Now, we start instantiating the complementer, adder and parity checker. See, the complementer as we have earlier designed, there we had specified the parameters in a particular order. First one is the output, second one is the input vector, third one is the control. So, here also when you are instantiating, the parameter ordering is kept the same. B out is the output, B is the input, at sub is the control. So, this you can again refer to this diagram. B out is the output, B is the input, and at sub the signal is coming, right. Now comes the adder. See, with respect to the adder, the outputs will be this intermediate sum and carry, and the inputs will be A, this B out and this at sub, right. So, you see this adder. This adder will have sum and carry as the outputs and A, B out and at sub as the inputs. Similarly, the parity checker. Parity checker will have one output P and the input will be sum and carry. See, the way we have defined or declared the parity checker, we have accepted only one single input, 9-bit input. So, the input will be the concatenation of these two. So, you see exactly we have specified in that way. Parity checker takes two parameters, one is P, other is the concatenation of carry and sum. So, once we instantiate these, the interconnection between these modules get automatically defined, right. So, this example shows how we can create a design hierarchically. Starting with the low level modules, we can get a design at a higher level, we can go up step by step. Now, given a problem, you can structure or you can divide up the problem into smaller sub problems, you can divide the modules into sub modules. In that way, developing a bigger design hierarchically is a good idea, you should design it that way. But once you have designed, you will have to check whether the design is correct or not. So, typically the first step you go about before actually trying to synthesize is to simulate and find out whether the code you have written is functionally correct or not, because this code was translated from some kind of description, behavioral description or some kind of block diagram something. So, in order to check whether your coding is correct, you will have to go for simulation. Now, for going for simulation, you will have to write the so called test bench that I had mentioned earlier. So, you will have to write a test bench which will be applying the inputs to the module you have written, and it will also accept the output and either compare or store the output in a file or display it on the screen something. So, in our next lecture we will be primarily looking at how we can write the test bench and what are the different features available there, because writing test bench will be required not only for behavioral simulation, also after you have carried out the synthesis, you have the gate level netlist possibly. There also you will have to simulate and you will have to possibly compare the behavior with the netlist. So, you will have to run the simulator twice and then you will have to compare and find out, right. So, I think all these things we will be discussing in the next class. Thank you.